Okay, so if you remember the last lecture, we studied about the generation of femtosecond lasers, or you can say ultrafast lasers. So there are the important thing in the generation is mode locking, and after the mode locking, you have to manage the dispersion because of broad spectrum, and there is a standard configuration which I showed in the last lecture for femtosecond laser generation. In the cavity, there are two prisms to compensate the dispersion. And that is the important thing. And the mode locking, what kind of mode locking? If you remember, that is Kerr-lens mode locking happens in most modern lasers, TICEF type. And today we are going to study some mathematical equations. I'm not going to solve the equations. So these equations are supposed to be used if you want to calculate, if you want to design the oscillator somehow. So let's move to the okay, so what do you see here? It's a design consideration. Okay, design consideration, and specifically femtosecond laser oscillator. There are three, the key equations which we need to apply if we want to design an oscillator. So here, if you see, the first equation is mode locking condition. Okay. This equation is two things you can see in this equation, tau p and nu t. So the first thing here, what it shows the gain bandwidth. Okay. And second thing, it shows the pulse duration. Okay. How long the pulse, for how long the pulse appears. So that is pulse duration. And equal to greater than this value, which is for the Gaussian ideal case of the beam or the beam profile. So it's in general, this one is called time bandwidth relation. Okay. And there are two possibilities. Here, if we don't use this G, then it will be a time bandwidth product, but that bandwidth will be like the bandwidth of the special or the spectrum. Like if you have here, this is your wavelength here, and this is your intensity, wavelength or frequency. So this bandwidth Okay, but here G is mentioned, so that G is linked with the gain bandwidth, the gain of the material or the gain medium we use. Okay, so this one here is not this one. Okay, it's a gain bandwidth. And pulse duration is obvious. This one is pulse duration here. If you see the bandwidth, full width, half maximum of the temporal profile. So if this equation is satisfied, okay, then we can have mode locking condition satisfied. Like if this condition is not satisfied, then it means mode locking cannot be achieved. Okay, and definitely, I mean, we assume or we suppose in the beginning that what pulse duration we want and what material we are using and what is the gain bandwidth of that gain medium. So if it satisfies this condition greater than equal to 0.441, then it means we can achieve the mode locking. If this condition is not satisfied, then we cannot achieve mode locking. And the mode locking is one of the things which is necessary to generate the femtosecond or the short pulses. Okay, so this is the first key equation. Now move toward the second one. Okay, this is this simulation. It will show that the one side, if you see here, this one is temporal profile, and here if you see, this is gain profile, gain of the gain medium. Okay, so actually if you remember my previous lectures, or if you have been to my previous lectures, I mentioned that that broader the bandwidth, shorter the pulse. And if the bandwidth is not broad, then the pulse will not be a short. So this is what this simulation actually it shows. If bandwidth increase, then pulse duration reduced, and if bandwidth is decreased, then pulse duration increased. Okay, so this is related to the design consideration equation, first one, which we just studied. Okay, so this equation now here, equation 2 you can say as well. This is linked with the pulse duration. Okay, the sequence I'm showing here, equation 1, equation 2, sequence can be changed. It's not important that it's not a hard rule. I mean, the sequence has to be like this. So in this equation, if you see here, we have pulse duration, okay, and this pulse duration obviously is the pulse duration of the femtosecond or whatever pulse is generated. But here we are specifically discussing about the femtosecond laser oscillators. What other things in this equation, if you see the lambda and delta lambda. So this lambda is obviously the center wavelength. Okay. And this lambda bandwidth here. Okay. So spectral bandwidth. So what you will calculate here, you will calculate the pulse duration. Okay. What wavelength we have, and or what wavelength do we want. So according to that, you can easily calculate the pulse duration. So, but only to calculate the pulse duration is not enough. The oscillator, or from where the pulse is generated, is supposed to be mode locked. Okay. Now, if you see on the right side, this plot, what this plot is showing on the x-axis, if you see here, it's a spectral bandwidth. Okay. And on the y-axis, what you see, the pulse duration. Okay. What it shows actually, it simply shows that the pulse duration is inversely proportional to the spectral bandwidth. Gain bandwidth and spectral bandwidth actually. In both cases, the pulse duration is inversely proportional. It's not directly proportional. Okay, it's opposite. So if the spectral bandwidth is increased, the pulse duration will be decreased or reduced, and vice versa. So what it shows here, if you see here, if the spectral bandwidth is like, let's suppose is here somewhere, and then you can see the pulse duration is pretty much high or something like this. So anyway, this plot, it shows that the inversely proportional relation between the spectral bandwidth and the pulse duration. Now we move to the third one. Okay. Cavity length. Cavity length. So cavity length is the most important thing. Okay. So if you see here this equation, L is equal to C over 2 frequency. Okay. And this frequency actually is, if you see the subscript here is rep, it means this repetition rate. Repetition rate. And this frequency, I mean, it can be like, you can write like this is okay. No problem, because in the previous slide I used the nu and here I'm using the f. So that is why I need to mention this thing. So c is the speed of light. And so basically what repetition rate you are expecting, or you calculate, or you are designing for, according to that you can calculate the length of the cavity, or vice versa. If you have in your mind the length, you can calculate the repetition rate. But usually repetition rate we assume, so it's some standard values of this repetition rate, 80 megahertz or something like this. Now on the right side, if you see here, this is the typical configuration of the femtosecond oscillator. And this femtosecond oscillator, I explained in the last lecture. So you people can go back and see. This starting from here, okay, and here, and here, and here, and here, all the way. This is the total length of the cavity. I explained in the last lecture that we need this prism for the dispersion compensation in the oscillator. And for pumping the crystal, we need to have a certain arrangement like here. Okay. And prism are supposed to be adjusted at certain angles to compensate. So the red portion, if you see the red line here all the way, This is the path of the beam which is generated in the cavity, and this whole length is considered. Okay, and it passes through crystal and passes through the prism and etc. Apply this formula, speed of light and what repetition rate do you want, after how long the pulse appears. So if this is a pulse here, okay, and this width will be the pulse duration, and this difference will be the repetition rate. Repetition rate, or like I'm telling in the form of frequency here, so 1 over t. Okay, so after how, if you say, if you say in terms of time, that the difference between the two pulses, the time difference between the two pulses to appear, and you can calculate its frequency, that is the repetition rate. Okay, and that repetition rate is very important, and usually it depends on many other factors as well, and which I don't feel necessary to discuss here. But in general, we take 80 megahertz, 75 megahertz or something like this. Now let's move to the next slide here. What other thing we are considering, that is dispersion management. Okay, whenever you design the oscillator, whenever you make the oscillator, then you have to think about the dispersion there. Definitely you will insert the prisms or whatever other arrangement to compensate the dispersion. But this equation is very important here to know. That is called Selmier's equation. Okay, and this equation is relating what it does actually, refractive index and lambda. It relates the refractive index and lambda, and all the others like ABC, BC, basically B and C, these are the constants, or it is called the Selmier coefficients. And it depends on the material. When you buy the material, with the data, usually it comes these values. So this equation, dispersion introduced by the prism, which we are using to compensate actually, it can be described with this equation, because the light passes through, and each and every material has a refractive index, and this refractive index is linked with the wavelength. For some wavelengths were different, and for some wavelengths it's different. So basically this equation showing the or relates the refractive index and wavelength. Okay, so now if you remember in the last slide, we discussed about the group velocity dispersion, group delay dispersion as well. Okay, and the equation which is introduced by the prism or any other material, actually, and here I'm specifically mentioned the prism. So in this equation here, you have this group velocity dispersion, which is also called GVD, and this is the standard equation for group velocity dispersion. And here this is a wave vector, and the omega is angular frequency here. Okay, so group velocity dispersion, when thing is moving through any medium, dispersive medium, then definitely this effect happens. Okay, and this equation is standard for this one. Pulse broadening. Why pulse is broadened? and this pulse is broadened because of the dispersion, and this dispersion happened because of the dispersive elements. Okay, and like here, this equation, what it has, just a minute. Okay, so what it has here, that delta tau here, tau naught over 2, and this is the partial differentiation of the d lambda and delta lambda. So obviously T naught is the pulse duration, okay, and this one, and delta lambda is obviously the spectral bandwidth, and here this term, this differential is a derivative of the group velocity dispersion, okay, and with respect to wavelength, okay, that is the angular frequency above, and this one is wavelength. So pulse broadening, how much pulse can be broadened? How much a pulse can be broadened? So this equation will tell you, okay, this thing. And if we go to the next slide, there is a plot there. This plot, what it shows, that this one is plotted the spectral width and pulse broadening, delta tau, okay, and we fix some values, okay, these GVDs, 3 values, okay, 0.01 picosecond per nanometer square, 0.1 picosecond per nanometer square, and 0.2 picosecond per nanometer square. So obviously in all the cases, if you increase the spectral bandwidth, the pulse broadening will also happen. So it means the pulse will also get broadened, or not? What do you think? How many people are there today?
Yes, sir. Pulse gets broader.
Is it different from pulse duration?
Sorry, who is saying? Come again. Come again. Who was there? What exactly this plot is showing? Gazanfar. Gazanfar, are you there? Gazanfar, can you hear me? Amna Said. Amna Said, can you hear me? Oh, I think I don't know. All the time is net problem. Eduardo, you are here today. Eduardo, can you hear me? Nargis Ghafoor, can you hear me?
Sir, I'm here.
Okay, at least you could listen.
Sir,
So, yeah, go ahead.
could I answer?
Yeah, sure.
Okay. Sir, what I am getting from this graph is that the pulse broadening is increasing because of dispersion.
Okay.
When the dispersion is happening in
Yeah.
the material,
Okay.
With the passage of
Okay.
time, the
Okay.
pulse broadening is increasing.
Okay. And the spectral bandwidth, the spectral width along the x-axis?
Spectral bandwidth along the x-axis, it's also increasing.
Yeah. So we are discussing here pulse broadening, not
Yes.
the pulse duration.
Pulse
Okay.
broadening.
Yeah.
Yes, sir. Pulse
Yeah.
broadening.
Okay. So don't get confused. Okay. Thank you, Naresh. Thank you very much. So the thing is that this plot, basically it shows what we have seen or what we have learned in the last slide, this equation. Okay. So this equation. Okay. So keep in mind. And so on this side, there is a pulse broadening, and this side is spectral width. And these are different dispersion values, like green is higher, definitely. And then it comes a blue, and then it comes a orange. Okay. So it's obvious that spectral bandwidth or the spectral width is increasing, pulse broadening also increasing. Okay. It's not a pulse duration, it's pulse broadening. Okay. So these are the key equations actually, what we have studied. And now, these equations, keep remember that if you need any time in your life somewhere, so these 3-4 equations are very important. Okay, in case of femtosecond lasers, first is a bandwidth, time bandwidth product, and then just a minute. Okay, then this one is the pulse duration. Okay, this equation, and after that that somebody's mic is opened, I think. Can you please close the mic? Adnan Sami, your mic is open.
Or maybe you can close it.
Let me check if I can. No, I cannot. Problem is that he's not listening. Actually, he's somewhere else, but he let it here like this. No, I cannot. Anyway, so the thing is that, and this cavity length. Okay, so these equations, if you need a very simple oscillator to build or something like this, and then after that, you have to think about the dispersion. Okay, and how much dispersion you need to introduce to compensate the dispersion already in the oscillator. So what to introduce? Prism, what kind of prism, at what angle, so that you can compensate. Okay, so now what is our goal actually? That we generated the femtosecond laser. Okay, and we know how to generate it. Now our goal actually is to amplify, because in case of just oscillator, the energy, or you can say the peak power as well, or the intensity will be very low. In some applications you can use, but not most of the applications. So you need to amplify it. This is the ultimate goal. And if you see this equation here, amplification, what it will do? Increase the energy, but in the way we are supposed to do, that to increase the energy, but the pulse duration should not be increased. Okay, so controlled. And what this equation is showing now, that is the peak intensity is equal to the pulse energy here, and A is a beam area, and this T is a pulse length here. Okay, delta T. Delta T is a pulse length here. Okay, and this relation, intensity is directly proportional to the pulse energy and inversely proportional to the pulse length and the beam area. If the beam area is increased, then intensity will be reduced. Okay, so if your peak intensity actually is inversely proportional to the beam area, so beam area has to be controlled. Okay, and other thing is that IP is directly inversely again, sorry, with the pulse length. Okay, and this IP is directly proportional to the energy, pulse energy. Okay, so the pulse energy increase, intensity definitely obviously increase, but if the pulse length is increased, then intensity will be reduced. Okay, pulse length is the same thing like for how long the pulse appear. Okay, and so we need to have maximum intensity, maximum possible intensity for a certain application or whatever it is. And for this one, you have to take care of the pulse energy, beam area, pulse length. Okay, and what the animation or the simulation on the right side, it shows, it's very simple. That heat plot is pulse duration here along x-axis, and you have beam area along y-axis. And what it shows here, you can clearly see that it's a peak intensity. So here, this portion, if you see here, yellow portion. So here the peak intensity is maximum. So why it's maximum? Because the pulse duration is very much less here. Okay, and beam area is also less here. So if you go up here like this, so definitely the pulse duration will be increasing and the beam area will also be increasing. But the intensity here is reduced. Okay, so this just to visualize or to show you people that how it could be. So we need to have a maximum possible intensity. It means maximum possible energy as well. And for this one, we have to take care of the things which is beam area, pulse length, and the pulse energy. Okay. Now, if we move further, this is maximum average power. In some cases, we actually need maximum peak power. But anyway, here we are discussing about the maximum average power. Because in case of pulsed laser, usually we do not go for an average power. We take the peak power. Anyway, this thing is also necessary to understand here. This, the average power is directly proportional to what? Energy, pulse energy, and R. That is here repetition rate. Do not confuse with the previous equations, okay, which I use for the oscillator. Okay, so this R actually is a repetition rate. This we are studying about the amplification. Okay, so do not confuse with the oscillators. So the P average is directly proportional to the pulse energy and is directly proportional to the rep rate. Okay, so more repetition rate, average power will be increased, and more energy, definitely average power will be increased. So if you have like this pulses like this, whatever the rate, I don't know, megahertz or something like this. And if you have like this, so definitely in this case, the average power will be more than this one. Okay, because the frequency here, the repetition rate is higher as compared to here. Okay, and the plot on the right side, it also shows that the repetition rate and versus average power. Okay, and at different energy, 1 microjoule, 5 microjoule, 10 microjoule or something, it is plotted. So you can see that the repetition rate is increasing here in the case of 1 microjoule. And so you can see the average power will also be increasing, even though it's a little increase. But if we have like 5 microjoule here, then you can see the repetition rate is increasing and the average power is increasing more sharply as compared to this one. And if we increase more the pulse energy here, that is 10 microjoule, then this is very prominent increase. And it shows exactly the proportionality. Okay, so this is these plots actually, in my opinion, may help you to understand these equations. And why these equations are important whenever you study the ultrafast laser, these equations are important to know. Okay, and some more will come later on. Now, what do you see here? Do you know that we need a pump to generate? We need a pump laser, okay, in case of oscillator, to generate the femtosecond or ultra short pulses. But this pump we also need in the amplifier as well. Okay, so what does it mean that if you have oscillator and then you have amplifier, and then if may need to have another amplifier if needed. So you need a pump here. You also need a pump here. And you also need a pump here. Okay. So without pumping, amplification will not work as well. And without pumping, definitely oscillator will not work as well. Okay. So how many stages a laser system is having? You need the pump laser. And here you can see very clearly the energy level here. That is your generation of the laser, and the green one is a pump. Okay, and similarly here, this is your oscillator, and this is your amplifier, and you need a pump pulse. One thing you have to keep it in mind. If you are, in case of ultrafast laser, for the pumping of the amplifier stages, you need a pulsed pump laser, not the CW. Okay, and it should have a longer pulse, what we are supposed to generate with this amplifier. The pump laser, it should have longer pulse, and like here you can see, and longer pulse, and usually in the nanosecond range. Okay, as intense, it has to be intense. Sometime it happens that we use a one pump laser for the two amplifier stages, but it depends. But in any case, for the amplifier we also need the pump laser, and for the oscillator we also need the pump laser. Okay, and this one, in case of I mentioned many times, for this titanium sapphire laser we need a green color pump. Okay, so green colored pump is because it depends on the absorption band. If you remember, or if you go back to my previous lectures, maybe you can understand somehow. So okay, so move further. What do you see here? There are different kind of amplifiers, or amplifier configuration can be used in the ultrafast laser. Okay, and this one, like, it depends. Some amplifier configuration, they have advantages over the other kind of amplifier technique or configuration. So if you see here, this is the basic concept. I mean, if you see, this is your gain medium, which is TISF in our case. Okay, and this mirrors, and this green one is pump laser. So you have to pump, and this one is coming, input is coming from the oscillator. Okay, and output can go anywhere, wherever you want. Okay, but we'll study what will be after that. So this is the basic configuration. What is the basic thing in this amplifier? That the beam, input beam, is supposed to pass number of times from the crystal. Okay, and this beam should pass from the crystal number of times, and it should pass through the same point, same area. Okay, it should not be like if you have crystal like this, and one is passing like this, other one is passing like this, and other one is passing like this. No, all, if you have this point, then all pass through from here. And this is the critical thing in the amplifier alignment and designing. It is not easy to make a beam to pass through from a crystal and same point, all them. I mean, okay, this one is like a 4 passes or something like this, but sometimes we need to have like 12 passes more. It depends. I mean, how much amplification do we need? Okay, so now here I'm just writing the multi-pass amplifier. Other kind of amplifier exists, that is I'm not covering here. We call it regenerative amplifier. I don't feel that it's necessary to discuss here because it's a little bit advanced way to understand regenerative amplifier. So I'm only discussing here the multipass amplifier. So multipass amplifier, As I explained, this is the basic concept. And there are types in multipass amplifier also, like bow tie type. So bow type, I mean, like it's like this. If you have seen the bow tie, okay, and the ring type, the closed circle, or some this kind of arrangement. So what you see here, this is just to show you that this is the TISAF crystal, like is mentioned here, and this is the input beam from the oscillator, okay, and this green one is a pump beam, which is also passed through the crystal at the same point where the laser beam is passing through, okay, the TISAF crystal, and the pump and the input laser from the oscillator, it should pass through the same point from the crystal. And definitely at the other end you have the amplified pulse. This figure or the diagram, it just show you how it can be. I mean, if you imagine that there is a crystal and the laser beam is passing through and where the pump is passing through, or something like this. Ring type. So ring type mean it's not exactly like it's a ring. No, ring type mean that it, like here you can see the beam is entering from here, okay, and then it moves here and here, pass through the crystal, then here, and then here, okay, and then after number of passes it goes out. So this kind of arrangement, but in any case all the passes should pass through the titanium sapphire crystal at the same point. Usually the crystal is not very, like it's not very big size, it's very small size, and critical, and it's very critical to make it pass through all the passes through a simple, very narrow area. Maybe in your mind you may think that what is this PC is a focal cells, and after the oscillator the focal cell is used because to select the pulses. It's not possible. I mean, oscillator, the oscillator, femtosecond oscillator, it has a repetition rate 80 megahertz, we assume, or 40 megahertz. Even in case of like you can say it's a 40 kilohertz or something like this. We cannot amplify with such a high repetition rate laser pulses. Okay, so oscillator generated the pulses with a certain repetition rate. Then we need to select the pulses from these, and we decide, okay, we may need one pulse after 100 pulses, or one pulse after 1000 pulses. You select. You cannot amplify each and every pulse. Okay, so keep in mind, you cannot amplify each and every pulse. So that is why this focal cell is used, and it has a controller outside box. If you remember, I taught about this focal cell and Kerr-lens and these kind of things in the previous lectures. So this focal cell select the pulses. It's up to us, and also the depend on the focal cell how efficient it is. And important thing is that we cannot amplify if the pulses from the oscillator is coming 80 megahertz repetition rate or 40 megahertz, we cannot amplify. Okay, we have to select. So we decide with this one. Let's suppose now after entering the passing through this focal cell, the pulse's repetition rate is kilohertz. Okay, so kilohertz from megahertz to kilohertz, from 80 megahertz. And okay, let's suppose we go to the 100 kilohertz or 1 kilohertz or something like this. So this focal cell actually, it selects the pulses, and then these pulses are amplified, and we have a repetition rate after the amplification that is like 1 kilohertz, 10 kilohertz, or whatever. It depends on our focal cell adjustment, but it cannot be megahertz in some cases, but not this kind of configuration. Okay, so move to the next slide here. This is also ring type. This is experimental, true experimental setup actually. And this one you can see here how the pulses are going here. This is your input pulse here. Okay, and from here it goes here, and here, then here, then here, then here, and then here, and here. So each and every time it passes through the crystal, but it's making the round. Okay, it is called ring type as well. It's not like a ring, but it is called a ring type. And you can see here, this is the pump, and both sides pump here. Sometimes it's from both sides, sometimes it's from one side. It depends on the configuration. So there are some, I mean, like here is input, and here you take it out the beam. Okay, and it depends, I mean, like what configuration we have. Okay, so these are the exact parameter of the amplifier. Use a 45 centimeter, the concave mirror. This one is also concave mirror here, and mask. It helps to make possible the passes to count and make possible, so that it's easier to understand that the passes are passing through this mask first, and then to the crystal, that how many passes are passed. And after that, this is bow tie type. So bow tie type is not a ring type. So what exactly happened here? If you see here, this is the input. Okay, and this is a focal cell which decides the pulse, and then from here, these are the mirrors, concave mirrors, curved mirrors, and it depends. Sometimes we need to use a plane mirror as well. And this is your crystal, and this one is pump. So it enter here, then it goes here, then pass through the crystal, and from here, 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 here. Okay, so it makes like something like probably 6 passes or something. Okay, so this is bow tie type amplifier. Okay, amplifier is essential part of the ultrafast lasers. Okay, first one was a ring, and this is a multipass amplifier. Usually, for your information, probably the first stage in case of ultrafast, I mean, like a reasonable lab, it has 2 amplifiers. So 2 amplifier, if you have a 2 amplifier, then the first one is a ring type, and the second one is bow type to boost the power. This is usual way. This is, you can see that now this is a bow tie type amplifier, and you can see here, this is the crystal here, okay, and these are the mirrors, both sides here, and here these are what you see here. These are pump lasers. It's a high power amplifier, and it has so many pump lasers, and you can see this color, green one. This is a pump laser beams. Okay, so it's pumped this type of crystal, and you amplify. It's usually, I think, it's around petawatt peak power or something like this. This is the configuration. The purpose to show that you can see that how it is look like, or how it is configured. Pump laser. So pump is very important, as I mentioned that, and this is one of the market or commercial pump laser. Okay, it's called Saga. Its name is Saga, and this pump laser, this has ND YAG inside. Okay, and ND YAG actual wavelength is IR region more than 1000 nanometer, which is not at all suitable to pump the titanium sapphire. So in this case, what we do actually, as I mentioned in my previous lectures as well, we use the second harmonic generation crystal to convert this 1064 or whatever it will be to half. So what we get at the by using this second harmonic generation crystal, and what we get 532 nanometer output, okay, which is essential to pump the titanium sapphire. And just for you people to know that this pump laser, its specs are like 1.8 joule energy. This is also pulsed one, and there is another one which is more higher power pump laser. It can give 16 joules. Atlas, there's some examples actually, just to. But anyway, the purpose of this slide to show that this LBO crystal is used to convert this ND YAG's actual the first harmonic, actually the actual wavelength, to the second harmonic. Okay, so which is the green one. Okay, so here, if you see here, this is just to show you how titanium sapphire, I mean, it looks like, you can see here. So it is like this. You can see on one side is a rod form, and other form is in both the cases it has a Brewster cut. Okay, and this small crystal, actually it's very expensive, and it's polished and very carefully doped actually. On the right side, if you see here, this is a green light, but you see it's a pump light. Okay, so this green one is a pump, and the rest of, it's not very clear. Maybe later on, some other day, I will show you the longer video properly. Here, somewhere is a crystal here, and this green one, and something like this. Oh.
Ladies and gentlemen, it's Blind Days. And here
Okay, let me share again. Okay, so you can see now. Okay, so now what you see here, some mathematical equations. So these mathematical equations, probably you may know before, but when we study the amplification, we need to know these equations. So what this equation is showing here, this one, this is output intensity, input intensity, and exponential of GL. So G is a gain, coefficient of the medium, and L is a length of the gain medium. Okay. So this equation is specifically related to the gain medium, whatever we use in case of amplifier. And on the right side, you can see the plot. This plot is length versus output intensity. So the length increases, output intensity also increases. But this is very, very, very simplified case. Actually, it's not like this. Okay. This is very simplified kind of case that the output intensity is increased with the length of the gain medium. Okay, which is not the case in actual practice. Here on this slide, what you see, this is more practical equation. Output intensity and input intensity. But I saturation, what is ISAT? I saturation is the saturation intensity of the medium. The gain medium, it has a limit. When you buy, I mean, in the data sheet usually is mentioned. I saturation is the saturation intensity of the medium. This is the limit of the medium actually. So at certain value of intensity, it becomes saturated and it's not causing the amplification. Okay, that is, it's called the I saturation or ISAT. Okay, and in the real amplifier, we have to consider this thing. This gain saturation or intensity saturation is also called the gain saturation, because at certain value of the intensity, the crystal or whatever the gain medium is not able to amplify further. Like intensity is not increasing at the output. So, and you can read here, it's mentioned that saturation intensity is that intensity at which the gain medium experiences significant gain saturation. Gain saturation means it's saturated. And at that point, the efficiency definitely is reduced. It cannot amplify efficiently. Okay. And this management of saturation intensity is essential to understand. So that is why this equation is important. And if you see the plots on the right side, these plots, you can input intensity on the log x-axis, and here they have output intensity. Okay, I in over IT and I out over I set. So there are four plots actually, and different GL value. G is again L is the length. Okay, so starting from here, this is a yellow one 3, green one 2, and the blue one is 1, and orange one is 0.5. So what do you see here? That in case of orange, which is 0.5, GL 0.5, there is an increase in the output intensity with the input intensity, but that increase is not that much. Okay, and but if you go further, like maximum one, the yellow one here, then you can see this significant increase in the intensity. Okay, but considering this high saturation also, so at certain, if you see here that even though the intensity is increasing here, but the output intensity is not increasing at certain point. Okay, here if you see, almost there is increase, but not that much as compared to in the beginning. This increase is rapid. After that, this increase becomes slower and slower, and at certain point, the output intensity is not increasing that much, even though the input intensity is increased because of this gain saturation. Okay, gain saturation. The gain saturation, obviously, if I say gain, it means it's related to the gain medium. Gain medium is titanium sapphire is the gain medium. Okay, and this thing we are specifically discussing for the amplifier. This is how you can calculate if some values are given. You can see here this input intensity is 10 megawatt per centimeter square, and gain coefficient is 10 per centimeter, length is 10 centimeter, and saturation intensity is also given, which is 100 megawatt per centimeter square. And for the practically, I mean, if you want to design amplifier, if you want to make amplifier practically, then you have to consider this saturation intensity, gain saturation concept. It is must. Okay, so if you substitute these values here, and you get these values, this calculation, some steps at the end, you get like 9650.92 megawatts. Okay, so per centimeter square, how much was input intensity? Initial intensity was 10 megawatts. So from 10 megawatts, it's 9600 megawatts almost. So this is, if you use this equation, then how you can calculate how much intensity at the output we get if the input intensity is whatever the value is given here. So amplification process calculations. So amplification process calculations, actually, the key parameters for this one is initial pulse energy. What is initial pulse energy, and what will be the output pulse energy? Small signal gain, the gain provided by the amplifier. When the input energy is low, and saturation energy, same like saturation intensity is saturation energy as well there. The gain start saturate. This is the saturation energy. And gain bandwidth, this is the gain bandwidth here, the bandwidth over which the gain is effective, the gain medium. So this we know, and we need to calculate this one, and we have these parameters, or first we need to know these parameters. Small signal gain may come with the data, like if the energy is very low in the beginning, then what will be the gain? And saturation energy, what will be the saturation energy? It's corresponding to the saturation intensity. And what is the gain bandwidth of the gain medium? So we need to know these things to calculate this output. Okay, first we need to find out the gain saturation. If we know these parameters are okay, but if we don't know these parameters, then we have to find out these parameters, these. Okay, so that is why it started from the gain saturation. So gain saturation, the formula you can see on the right side here, that is G is equal to G naught exponential E over E saturation. So gain of the amplifier decreases, as I mentioned to you. It's because of the saturation. Intensity is decreasing, it means that energy will also be increasing, because intensity is directly proportional to the energy. And when the pulse energy increases, then that certain value, it will not increase that much because of the saturation. And the gain of the amplifier, it means the gain is decreasing. As pulse energy is increasing because of the gain saturation, there is a gain saturation value for each and every gain medium. So in this case, the pulse energy decreases due to the saturation. Now the plots, I mean, if you can understand these plots, on the left side, that is the important one. What you see here, that E over E saturation along x-axis, and what you see here, that is the gain, normalized gain, you can say G over G naught. So if you go back, so small signal gain is a G naught. Okay, so G over G naught, so actual gain and small signal gain. So what you see here, if you start from here and it decreases, pulse energy is decreases as gain is also decreasing. So gain is decreasing, and here the pulse energy is increasing. So what exactly it shows, that if gain, normalized gain is 1, and here your pulse energy is 0, and if you come here at this point, then it means something here, and then here it's like this, and here it's like this, and here it's like this, and here it's like this. Okay, so the gain is reducing here, but the pulse energy is increasing. So when the gain is going to be maximum, then the pulse energy is reduced because of the gain saturation. And here on this side, pulse energy and normalized gain But some factors are fixed here. That is E is equal to 2E naught. And this E naught is initial energy. E naught is initial energy. So the E is output energy here. And this E naught is initial energy. So ratio of this one, E over E naught here. If E is equal to 2E, if twice the input energy. And what thing you notice here, that is normalized gain here. And this is the pulse energy at the output. Okay. And you can see here the value, what value are changing, G over G naught here, and this E over E saturation. We don't have E over E saturation. E over saturation, we have fixed values. So with the change of this one, this curve is changed somehow, but the pattern is same. Pattern is same. Okay. I hope you people can understand this. Now, energy, amplifier energy actually. This is the equation you can see on the right side here. Okay. And this is your input energy, and this is your output energy, and this is your small signal gain, low energy gain. And L is introduced here. So this L basically is the length of the gain medium. This L actually is the length of the gain medium. So what you see here on the left side, input energy, output energy over saturation definitely. And this is your input. The plot is between this one and this one. Okay. And here you can see how the values are changing. In the beginning, this plot is like there is a small increase here, but after it reaches to the 4, then this increase is prominent with the increase of the input energy. Okay. And the output energy is increasing. And here actually this, if you see this portion, it's because we fix this value gain at this value. Okay. And that is why here you can see this portion is increasing, but not overall. But anyway, this thing is important. This plot is important to understand. That is just another parameter. I change another parameter to show something in a different way. But this one is more important here. This left side. Okay, so now if we have an example, we know these things, that initial pulse energy here, this one, and the small signal gain is 10, E saturation is 10 microjoule, and the length of the medium, gain medium, is 1 centimeter. And we are supposed to calculate EF and the gain, I think. That will be the next slide. Yeah. So first we need to calculate by using the previous formula. If you remember the previous slides here, you substitute the values here. What you get, this the gain value you get here. Okay, and then you calculate the energy. Okay, energy, substitute the value, and then you get the energy, which is 8 millijoule. And what is the input energy is 1 millijoule. Microjoule, sorry, 1 microjoule, and output is 8.8 millijoule. So this is how you calculate the things. This is how you decide the things. This is how you apply the formulas. And these plots actually is both the plots. I will not tell you anything about these plots. I may ask you in the assignment what these plots are showing, because these plots are exactly what we have calculated here. What is the behavior? What is the trend of these plots? Probably you may need to explain in your assignment. I will mention that one. So probably this is enough for today. I think it's for you people, it's really boring, I assume. And yeah, I will not move further. That would be for next class. And so, I mean, if you have any questions, you can ask, because today's lecture was full of with the equations or something like this. It's necessary to understand if you are taking this course somehow. Yes, David.
Okay, can you hear me?
Yes, I can hear you.
Excuse me, when the tubing of laser, the red one and the green one combines, it means that one laser is acting like a seed. I mean, they
Yes.
concentrate all together in one point to maximum the intensity and then pass through the sapphire glaze.
Definitely. I mean, the main TISAF laser, the red one, it's a seed. It is seed. And the next part of the question, I don't understand. You can say it again.
Okay. And in this case, because they are the different wavelengths, the red and the green one, how they combine, or they only
No.
converge in a point?
I think you don't remember my previous lectures. It depends on the absorption band. I mean, the wavelength doesn't matter. It depends on the absorption band of the gain medium. So that green one is absorbed in that one. That is why its population inversion happened, because of this pumping.
Okay, thank you.
Yeah, you're welcome. Okay, so anyone else? I'm pretty sure, I don't know. Mauricio, you have any question?
No, everything is clear.
It's clear, everything.
Yes.
So did you like this course? I mean, you are taking it?
Yes, it's well, it's very simple to it's a intuitive session, so I think it's yes, I like it because it's not complicated.
Yeah, okay. Actually, still you want to ask David something? Your hand is still there. Okay.
Sorry, I was.
Yeah, it's okay. I think Eduardo is there. I mean, it's your native, David. But I don't know. He just he's there or not. I don't know. He's not replying anything. Okay. And the thing is that this portion of this course, I'm trying to simplify many things, and also I'm omitting many things because I'm not making it very, you can say it's difficult. There are many things, I mean, in it which I may add, but I don't think it's because the background of the candidates here, they are not, they don't have very strong laser background. So that is why. Simplify. Still, I think it's pretty. Some of the topics are tough to understand, especially when you move to the ultrafast lasers. So, Sham, do you have any question?
No, sir, not right now. I will go through this presentation again and I will think about it.
Okay. Nargis, how about?
Yes, yes, sir, I'm here, and it was kind of a calculation, so it was honestly a bit easy for me to understand because I'm from the theoretical side of physics.
Okay,
But
okay.
it was right now I don't have any questions, but I think I would have because from the last 2-3 slides. But right now I don't even from the last third slide.
Okay.
Right now I can't even narrate my questions because
Okay.
I think if I would re-listen the your lecture, then I will get the point by myself.
Okay. Okay. Sure. Okay. So Eduardo is not replying. Definitely, I don't know. He's online or not. I don't know. Amna Said.
Can you hear me, sir?
Yes, I can hear you now.
No, sir, I have no questions. My internet connection was very weak today.
I don't know,
so
internet connection or what exactly, because whenever I ask you something, you don't reply.
No, sir, I tried to reply, but my internet connection was very weak.
Yeah, I mean, I don't know. Internet in Pakistan, I know that quite a bit problemsome, but do you have any question?
No, sir, I have no questions.
So how's your research going?
It's good.
You are doing some research or not yet?
Yes, sir, I am doing some research.
And definitely it's not related to the laser what you are learning here.
Sir, it is somehow related to laser.
Yeah, but that is simple kind of laser, but not that kind of laser, maybe for your future. Ali Hasnan. Ali Hasnan. Very good. Okay, so Zanfar will not reply as well. And today many people are absent actually. Anyway, a few more lectures and it will be finishing. Zanfar, can you hear me?
Yes, sir. Can you hear me?
Whenever I try to ask you something, you don't hear, or you don't pretend that you are not hearing.
No, sir. When you asked the question, my mic was not working. It's connected to other device. That's why I try to speak, but I think you are not listening at that time.
So, I mean, you were absent from the last lecture also. And
yes, sir.
And you did
Yes,
not.
sir. I went to my village. I didn't go through your last lecture, but this lecture is there are some things which I have to revisit and let you know if I get confused somewhere. I stuck somewhere.
Yeah, the last lecture also you need
Maybe
to go through.
Yes. Maybe that's why I not getting some things. So I will go revisit your last lecture, then I will come back to this lecture.
Okay, so and also you didn't submit your assignment.
Yes, sir. I am working on it. Inshallah, I will submit it tonight.
Yeah, I mean, most of the people, they are losing interest. I don't know. Anyway, so probably we will leave now. Let me try with Eduardo again. Eduardo, are you there? David, how do you pronounce this name?
It is correct. Like you say, Eduardo Gauna. Eduardo.
Eduardo Gauna.
Yeah. Yes. My sister, his name is Fatima. But you say
Fatima. Really?
Yeah. Yes. It is the same name of my sister. I think that it's very usual name in Pakistan country.
Yes. It is very common name actually. Very common name. By the way, you are arranged the live transmission also to the YouTube and or no?
Yes. Here every day I try to send the transmission.
Yes, I think only YouTube you can keep it, but not on the Facebook. I don't think many people are watching it. Nobody's watching. So only YouTube.
Oh, okay.
And with the proper title probably. And,
okay.
Yeah. Okay.
Yeah. Usually, then you delay that online recording and you upload the presentation because it's better quality.
Yes, definitely it is better quality. Sure. Even though I mean I don't have many viewers. Like last slide, just 4 or 5 viewers. The last lecture. So.
Sir, excuse me. Are both of you talking about your weekly meetings on YouTube?
No. We are not. No. We are not talking about our weekly. We are talking about this lecture. These lectures.
Okay. But how to join that? Because whenever I go for YouTube, I see it in a recorded version.
No,
maybe I'm a bit late.
No, that meeting actually the members only, but you are not the member. And in these days, we are not having that meeting actually. Okay. You want to be?
Okay. Yeah, I listened it a couple of times, but no. I don't know when the time is, how to join it. And
no, actually, in these days are not happening because members are not very serious in these days. I'm looking for serious members actually. So
okay, the members. Okay, I mean, members of your group.
Yes, I mean they are supposed to do something in that that what we discuss, some small project or something like this.
Okay.
So if you have any interest in optics and lasers, you can also.
I will see by the end of this course if I I find any interest.
Yeah. Okay. Because
now I'm gaining a little bit interest with your lectures.
Yeah, that's good actually. This is the purpose actually, is people to know and people to understand this in Pakistan, especially. I mean, very few people know about this kind of lasers.
Honestly, sorry, you are true. Yeah. Because honestly, in my PU, we don't have such facility. At least not my department. I don't know about the pure physics, right?
Yes, Nargis, you are right. Yes, you are right, because I also studied in PU. Out of question, these kind of things. I mean, mostly the theoretical stuff or the material science stuff. So this is, I think, it's kind of, I would say, it's a dilemma for Pakistan. None of the universities are teaching these kind of things. But in Mexico, I mean, David, they have so many places. Yes, David.
Hey. Yes. Also, your country is very well known in the world because you can fix anything. Even if a machine is broke, you can repair. Or I have seen many videos that you can build anything that your own machines, and also that you have a lot of technology. Is like the second country, the first is the India and then Pakistan, that have a lot of technology also around the world.
Reverse kind of engineering, I think. Anyway, so thank you very much, all of you, and hope to see you in the next class. And I don't know if that will be second last or maybe after that 2 more classes. Okay. So thank you very much for attending, and see you on the next Sunday. Okay. Goodbye and Allah Hafiz.
Allah Hafiz. Goodbye.
Goodbye.